So let's get warmed up with this. I won't play the sound because it echoes in the recording, but you can see exactly what this is. This is our introduction for today. We'll carry on still with fluid properties. I have a few announcements after we've gone through this at maybe 8 o'clock when people get going. But this is artificial surfing lakes, which exist. This is in Wales, south of, in the western part of the UK, which is actually a surfing area, the coast is. I used to go surfing there, not in Wales actually, but I used to go surfing, can I do that again? In the southwest of England when I lived in London when I was a student. I was a grad student, 22, and I could drive. Couldn't rent a car until you were 21. And so I was the most popular guy in town to drive people down to the southwest and then go surfing on the big fetch of the Atlantic Ocean as it comes all the way across the Atlantic and hits the UK. And so this is kind of an interesting thing to do. It's just a pond with some kind of wave generator in it. You can find these things in Australia as well, of all places. They're typically radial ponds with an exciter in the middle, kind of a tower that has these different segments where you can surf. And I guess you can control the wave format in some way by the stimulus you give it. And I guess the added advantage is that you don't get bitten in half by a shark, which I suppose is not a bad advantage to have it at some level. So, stop that. What else have we got? And this is pretty radical, I'd say.
Watch closely.
I guess I should have put So this apparently is off the coast of Portugal. There's an underwater canyon that focuses the incoming waves, and this is quite a repeatable wave that occurs, or set that occurs sometime every year, depending on the seas. And to me, it's just amazing that someone would do that. It's like coming down a mountainside that's moving, and I guess water can do you a bit of damage, of course, right? So it's just like hitting concrete in some respects, and of course, a bunch of water landing on top of you can damage you, bust your surfboard. That's the least of your problems, I think. So 80 feet, that's probably 8 stories, right? A normal story in a house is 10 feet. A 2-story house plus the roof is 30 feet of that order. So you get some appreciation from that. And so you might surmise from this that we're going to talk about waves today. So this is just to whet our appetite for this. What's this? Never believe anything you hear on RT. It's kind of an official arm, but this is interesting. This is a bridge in Volgograd, I think it is. And we talked about Tacoma Narrows Bridge last time. That's also a wave, a different kind of wave, of course. One that travels along a solid structure. And here, I'm not sure what the reason for this is, whether it's excitation by, I presume it's excitation by wind blowing across it at constant speed and giving this impetus, which we'll talk about when we talk about external flows around structures. It's absolutely explainable in terms of we can predict the frequency we'd expect to get given the velocity of the airflow. We won't do that today, but we'll do that, I think, in week 12. For those of you who are into renewable energy, wave power, of course, a number of different ways to do it. We showed a figure last time of an articulated float that moves with the waves, and the articulated joint you can set up if you can make something that turns this kind of motion into a rotary motion for a generator, which you can. Or you can capture incoming waves in caves, and the pressure increase in pressure that it gives is one way to be able to use that pressure periodically to be able to give power. Of course, predictable power, wind and solar are not so dispatchable, but wave power should be. Certainly tidal power is even more so. So you get the basic idea. Yeah, you get the idea. Waves come in, they crash through the system, and the exhaust from the air it displaces gets put through a generator, a turbine really, and turns generator and generates electricity. So, big thing apparently in the UK. You can have underwater windmills, of course, wind turbines as well. And what else do we have? And one of the things that we'll focus on today, actually this is a more interesting figure. It's kind of, I guess I have this underneath my hand, so it's and so we'll talk about the Japanese tsunami from 2011, from the big earthquake. The earthquake didn't kill anybody, but certainly the tsunami did. And probably in the video you'll see ships heading out to sea, as this Coast Guard ship is doing, and it's climbing up this incoming wave. This incoming wave is a crest, not so disastrous. You can see it's kind of peaking, but in the later movies you'll see that it's living up to its name. Tsunami apparently in Japanese means harbor wave, and it's just an inexorable rising of the water level, not a crashing wave, but inexorable rising of the water level, and driving everything before it. And so we'll look at that a little later. So that's kind of where we are. So it is pretty much 8 o'clock. So a couple of comments for the good of the order. Had some questions about the practice exam. Practice exam was really for last year because we'd never done an exam like this before. It's always been an in-class exam. And so that was just to alert people to how it is prosecuted. So you do the exam, probably be online, could be in this classroom as well. Should be ready to come into the classroom. I don't want to make you sit next to each other. You don't want to, given the health situation we're in. But that practice exam is really just to show you how to enter the data. And so you should do it. You can do it unlimited times. It doesn't count for anything. There's a solution for it there. It's roughly a half exam. It's a 15-minute exam. The real test will be 30 minutes on one day. You now have examples for that from 2020. I don't think you need to do the test now. You might submit the first homework a week yesterday, or midnight, just 8 hours ago, a week 8 hours ago, and then do it after that, because it'll be pretty obvious how we're doing this. And so I'd encourage you to look at that in due course, but I don't think you need to now. I think as we go through week by week and get through different material, you'll see that some of the test questions that you will see are doable by you. You have that knowledge. So I would encourage you to kind of keep up week by week and looking at those and seeing if you feel comfortable. Go through the actual test, see if you can understand the logic of what you would do, check with the solution, which is also posted, and to see if your approach is correct. And I think that's the best practice you can get to. Yeah. Yes, go ahead. What? Yes. No, I'm talking about the practice test. There is a practice test online, which you'll find on Canvas. And so 3 things you might look at. I mentioned download the homeworks, homework 7, edition 7. Download the past tests. First homework will be due next Thursday at midnight. I was pretty big about the fact that you don't need to buy the book, because we don't use any of the material specifically for the questions out of the book. But it's useful to have the book. If you don't want to spend $140 on the book, I'm guessing that you can hunt around for a 6th edition of the book, and you can find it online as a PDF. I'm pretty sure I've done that. Don't tell Wiley I told you that, but that's a possibility. And fluid mechanics hasn't changed much in 100 years. So these books the content is still germane. And that's any other questions for the good of the order before we get going. All right. Okay. All right. Well, we'll continue on our merry way. And as is kind of my proclivity, I recap some of the material that we've talked about in terms of what we talked about. So we're on the 3rd period. Last time we talked about definitions of density, viscosity, modulus. We'll talk about those a bit more today. We talked about the tremendous potential for dimensional homogeneity to be able to check your working, to make sure that your units are consistent across equations, and how to do that with differential terms and with integral terms, so you know how to do that. And we introduced fluid properties, mass and weight, you know. We talked about density. We began speaking about equations of state, which we'll take off from today, and we talked a little bit about moduli. So we'll talk about those, but then we'll continue to talk about these other topics. Wave speeds, viscosity, not really a static property, but a property nonetheless. We've kind of dealt with vapor pressures already on our diagram, and surface tension. So, in fact, I think the practice test, the topic is surface tension on that practice test. The venometer, actually, of how to be able to calculate what the alcohol content is of a fluid that you put in a venometer and exactly how it works. So you'll probably notice that these are, the written notes. These are on acetate from the days, I'm not sure if you even saw in grade school acetate. Certainly PowerPoint was around from the 90s onwards. So I guess you might not have seen acetate sheets that you put on a projector so much, but that's what these originally were. We talked about the ideal gas law. I think you've probably seen it. It's important to realize that these are absolute pressures and absolute temperatures. This is a component gas-specific gas constant, and this is density. Because of this relationship, if the temperature doesn't change when you compress something, the pressure to density ratio is always constant if it's isothermal compression. So if you compress it and you allow all the heat that's generated when you compress your bicycle pump to escape, then this relationship always stands, just because you can rearrange this equation as P over rho is equal to RT. Temperature doesn't change. It's the same gas that you had before, and so nothing's changed. If you compress it isentropically, and so in other words, with a insulation around the pump, so none of the heat escapes, so it changes the temperature in that particular case, then the pressure change is given by this ratio, with this being the ratio of specific heats, and this number for air is about 1.4, as you'll see in your text. And so these are actually taken out of Munson. And so if you can't understand exactly what I'm saying or don't follow it, go back to some of the videos or go directly to Munson. So that is kind of finishing off what we were dealing with there. So that is all we'll say about equations of state. We'll talk about compressibility. Compressibility maybe seems like an esoteric idea, but it's important for waves, believe it or not. And it's important for our understanding of, for instance, the yield of a gas reservoir. How much gas can you get out of a subsurface reservoir for gas? And so compressibility, maybe I'll do it here. I like writing things down as well, so, as you'll find. So maybe this is 1,3. And this is, so we're still fluid properties. And it will follow the stuff that was on the previous page, but I just think it's sometimes useful to write these things down. So compressibility. And so for gases, well, actually not for gases, but we'll do gases. By definition, so modulus is defined as the change in pressure that you apply to something divided by the change in volume per unit volume. So in terms of what that looks like, if you have a mass of gas inside a container, and your container is V0, and you change that volume by some amount, I'm just going to do this, by delta V, which is this here, and you have a pressure that's applied on this to do that, which is making the container smaller, and the container doesn't resist that pressure, so say it's a balloon, then this is the expression that gives you that. And so all it's saying is that if you apply a pressure, you change the volume relative to the original volume, and the constant that defines that behavior is called the modulus. This is a negative sign because when you apply an increase in pressure on the outside, this gets smaller. So this dV decreases as this one increases. And so to keep the constant positive, There's a minus sign. We can also write it in terms of the density, which is, again, keep the pressures versus densities separate. Change in pressure with change in density over the original density. This is density, not pressure. And the positive sign there is because when we apply an increase in pressure, the volume of the container decreases, the mass inside the container of gas stays the same, and so by the definition of density, mass per reduced volume, the density must go up. And so that's why that is this. So if you look at this behavior for a gas, we get an intriguing result. So if we take this modulus, and so we can also write this as being 1 over compressibility. Petroleum engineers use compressibility of a gas. They usually give it a symbol beta. And of course, the units of modulus are pressure, because these are dimensionless. The units of compressibility have to be the reciprocal of pressure. And so if we take this modulus for a gas, and we write it as equal to dP d rho, pressure divided by density, and multiplied by rho 0, then what we can do is we can take the ideal gas law. We can differentiate this. This goes to 1. And so we end up with RT. Right? This term here is this term. And we can rearrange this term in terms of, just by rearranging this, we get rho 0 is equal to, in the original gas law, is equal to pressure RT divided by RT. So this is 1 also, right? And so this term here, which is this, is just this. So I say it's an intriguing result because it says that the modulus of the air around us is just equal to the pressure of the air. Pressure isn't 0, it's absolute pressure. And so for air at atmospheric pressure, it's about 101 times 10 to the 3 newtons per meter squared, which is also a Pascal, which is also 101 kilopascals. Intriguing. I think it's an intriguing result. So immediately we know the pressure, the modulus, the compressibility of the air around us. It's true for up to relatively large pressures, many megapascals, but it breaks down ultimately. For liquids are termed slightly compressible. Gases are compressible. I guess the euphemism is highly compressible. Slightly compressible means that it's a linear relationship, not this relationship. So for liquids, E is often constant. And for rocks, which we're standing on, E is something like, say, I think I use 20 GPa, which is just for once 20 times 10 to the 9 newtons per meter squared, pascals. Water, surprisingly enough, is equal to, it's equal to 2 GPa. I think I'll go through an example here where I use 1, which is quite high, obviously much higher than water, right? This is kilopascals and this is gigapascals. So these are 2 orders of magnitude different from each other, 1,000,000 times. This is 100 versus 2, so I guess it's only 10,000 times different, but different nonetheless. Okay. And so we have magnitudes for this. So this is typically, so the idea is if you plotted a behavior for, all this is saying is if you plot, for instance, pressure with change in volume over volume, for gas it would be linear. If you give a pressure of this, it will give you a volume change of this. If you double the pressure, it'll give you double the volume change. I guess this should be negative, right? Because if you increase pressure, you're decreasing the volume. So that's modulus. Okay, that's perfect, right? So the reason that we're interested in modulus is because wave speeds relate to this. And so one reason that we might be interested in wave speeds, and we'll use, well, first of all, define it. Cp is the p wave speed. So if you put your ear to that, the end of the bench, and I hit it here, then you'd feel something in your ear. It wouldn't arrive instantaneously. It would travel as wave speed. It's traveling exactly the same process as you're listening to me. There's a delay between me speaking and you hearing it because of the speed of sound in air. This is the speed of sound in a solid, which is a wave. A different kind from a C wave, but a wave nonetheless. And so what we might do is, I guess I've used my stuff already. Yeah, maybe I can go here. I'll use this. So if you look at the compressional wave speed, Cp, it's approximately equal to what we've called the modulus divided by the density of the fluid. So if I knew what the modulus was of this bench and the density of the bench, then I could say something about what this speed was. The shear wave in an earthquake is the one which is like a skipping rope on the horizontal ground that you're shaking, that snakes along the ground. And it's roughly given by the fact that the shear modulus is equal to the modulus divided by 2 for a solid, but the shear modulus is equal to 0 for a fluid. And so the shear wave velocity in water just doesn't exist. But on land, the shear wave goes at something like modulus over 2 times density square root. And so those are the compressional waves that travel between you and me at speed of sound. Shear wave doesn't matter because air is, of course, a fluid. A gas. But what we're interested in fluids is also the celerity wave. And the celerity wave is proportional. You remember last time we defined the Froude number. I wrote it incorrectly, as someone pointed out at the end of the class. The Froude number was equal to the velocity divided by gz, square root gz. I corrected it on the video, by the way. By the way, you should shout if I have a wrong derivation. And so that is exactly what this is. This is saying that this velocity is equal to gz. And this is the depth of water. No physical property in this at all, of the water or the liquid, but just a physical property of the depth of the flow that's in there. And so these are the 3 waves that we're interested in. So what we could do, I suppose, and I'll just jump to a clean piece of paper, is try and look at what those would be. And so, So we know that the wave speed is equal to the modulus divided by the density. So we could look at the behavior for rock, for water, speed of sound in water, if you're talking to someone in scuba gear, and in air. And we could also look at the celerity wave. And so the celerity wave is equal to GH square root. So for rock, we said that the modulus, I've written some numbers down, hopefully, is 20 gigapascals. Newtons per meter squared. For water, what did I use? Do I use 1,000 just to be for convenient, yeah. So water, it's 10 times 10 to the, no, 1 times 10 to the 9. 1 times 10 to the 9. Bless you. And for air, it's 10 to the 5 pascals, right? 101 kilopascals. So the densities for these are all good numbers to remember. For rock, what did I use 2,000 kilograms per meter cubed. For water, you should know that probably. That's why rock doesn't float in water. And for air, it's of the order of 1 kilogram, 1.2 or something, I think. And so we can look at these wave speeds from that. So for rock, if you take rock, it's something like 20 times 10 to the 9 divided by 20 times 10 to the 2. Which should be about 1 times 10 to the 7 square root, which is about 10 times 10 to the 6 meters per second, right, square root, which is about 3 times 10 to the 3. So this is something like 3,000 meters a second. Which is about right. If you do the same for these, I've got it written down, so perhaps I'll just do that instead of, so we can concentrate on more the impacts of it. Water is about 1,000 meters a second, just keeping the numbers straight. Air is about 300 meters a second, 300 meters a second. And the celerity wave doesn't depend on these at all. Celerity wave depends on gravity, which is 10 meters per second squared, times the depth. Say for the example we're looking at, 1,000 meters. So that is 10 to the 3, 10 to the 4, square root. Square root of 10 to the 4 is 10 to the 2. 100 meters a second. Surprising, right? A surface wave on the ocean moving that. Of course, it's very small when it's out to sea. You saw it coming on shore with the boat going out past it, but nonetheless, it's moving quite quickly, but slower than these. And so this is the reason why you see lightning before you hear it. Speed of light is essentially instantaneous. What is it? 193,000 miles per second or something of that order. No, I'm switching units. And the speed of sound in air is 300 meters per second, which is about, I think it's 600 miles per hour. So order of magnitude, double these numbers and you get miles per hour. So 600 miles per hour is 60 miles per, it comes out to be about 6 miles per second. No, 6 seconds per mile. Sorry, you can do the calculation yourself. So if I get rid of this, 6 secs per mile. And so if you count the time between the lightning you see versus the sound you hear, 6 seconds means it's a mile away. 12 seconds means it's 2 miles away, etc. So it's a convenient way to be able to do that. So our reason for doing this is to be able to look at an example of, here, I think it's just a kind of curious example of, am I using this or am I using this? Yeah. Of why you might want to use it. So the idea is exactly this. And so if you look at the Tohoku earthquake, then in 2011, you see here, hopefully on this, and you can see on this as well, the Japan Trench. One plate goes down underneath Japan. It's the reason it has the volcanoes on the island. So in other words, if you drew a section across here, this would be the ocean bed, this would be the plate that goes down, this would be the ocean floor on the other side, and this would be Japan. This would be the water. And so the idea is that if you put, for instance, ocean bottom seismometers here that tell you when the earthquake comes, you relay that information on land by a cable, electricity. So this is the speed of light that this goes at, so it's instantaneous. So as soon as you get this, you have to process it to know it's an earthquake, use artificial intelligence these days to do it in less than a second, send the signal in, and you know that there's an earthquake, and the earthquake, this is about 100 kilometers. You know there's an earthquake 100 kilometers away instantly, and so you have time to do something. The wave that comes from this is going to be traveling at, what do we say? 3 kilometers per second. And to go 100 kilometers, it takes something like 30 seconds. Right? If this is 100 kilometers, then to go 100 kilometers to 3 kilometers a second, it's basically 30 seconds. The more damaging wave is a shear wave. The shear wave travels at a fraction of this, so maybe it takes 45 seconds to come. And so that's the time it takes for the shear wave, the damaging wave for the earthquake to come to shake the buildings, something of this order. And for the celerity wave, what did we say? It was 100 meters a second? Or 300? 100. Okay. So 100 meters per second. So if it needs to go 100 kilometers, then it needs to go 1,000 seconds. Is that right? And what's 1,000 seconds? So 60 seconds in a minute, 600 seconds in 10 minutes, so that's about 15 minutes, right? So you have 15 minutes to get to high ground. Of course, the standard procedure for getting out of a tsunami is to run inland and go uphill. You know, the retreat structures for that, since these have been happening, is go into a tall building that's above the floor that you're at. And so that's the idea of how you might want to, for instance, use waves. So let's look at something else. Well, you have this. I have this here. Sometimes this is a complex class because we have too many moving parts. So this is Kamaishi. I didn't show this earlier on. We've got other stuff to do today. But this is the port of Kamaishi immediately after the... You probably can't hear that, but it'll turn up on the recorded video. And so this is the instant the earthquake occurred. You feel it on land after 30 seconds, and you figure out what to do. Nothing's going on. You're worried about a tsunami. The boats go out to sea. The best place for boats in a storm or a tsunami is to go out to sea. You saw one climbing over the wave before, and you have to wait for the wave to come in. That's probably 50 seconds, so we don't want that. We said 15 seconds. Let it run. Doesn't want to run. Oh, it just looks as if nothing's happening. I guess it is running, right? So you see something on the horizon at the breakwater. I think it actually comes in at 20-ish seconds. You see stuff going on, to some boats, a little wave in there. That's not the tsunami. It's just a relentless rise in the tide, really. And then you look at these guys are in a parking structure, I think. This is a river that's coming out to the sea on the side, but now the tsunami is just inexorably pushing. It's breached the wall, the sea wall, and it's just filling up the town as it pushes inland, and it just keeps on going. And so I used to have that playing in PIP in the side as we went through the class, but I think that's just too distracting, so I haven't done that. And now, okay, the other thing I wanted to do is this, see if I can find it. Is this. This is just thinking about opening PowerPoint. Is it? Oh, it is. That's the talk I'm giving. That's not the talk I want. That's the talk I'm giving later today. After this class finishes. Must be this one. Ah, there you go. So this is a building in Tohoku, which is the site of the tsunami. A year later, I guess you see the whole thing. You see where it is. These are cracks in the high-rise building waiting to be repaired. Very orderly, the Japanese identified the cracks and patches to take care of the restoration. This is early warning. You can get it on your cell phone these days. This is circa 2012, but this is it. You get the signal from the ocean bottom seismometers. You get 30 or 45 seconds to do something. So in that, you could run out of the building. If you think the building's going to collapse, you could duck and cover, do whatever you need to do to get out of the way. So that's on cell phones these days. And this is just the utter destruction 1 year later, still not cleared up. This was on the anniversary of it, a day before the anniversary, one in 2012. Rice paddies still inundated with seawater. A school, 4-story school, where the tsunami, the height of the water rise went up 3 stories, but not 4. A car that's not supposed to be parked on top of a building. And you can look at these for other places. Some people, I have a movie, look up Mega Tsunami Wave of Destruction and see if you see a cameo of me on a Horizon documentary. There was a small tsunami in Indonesia at a volcano. Volcanoes collapsing are much more dangerous than tsunamis, than earthquake-generated tsunamis, because an earthquake is felt everywhere and detected, and so there's an early warning. If a slope collapses in the middle of the sea, this was Anak Krakatoa, which was the cone that grew up after the Big Bang of Krakatoa, the volcano in Indonesia in the 1800s. The bang heard around the world, I think that is referred to as, that ultimately killed 400 people when this small volcanic cone you see on the left here collapsed around Christmas time, went from this to this. And I think this is a cool little animation. And you can model these things using things more sophisticated than we'll learn in this class, but you can use wave theory to just be able to look at exactly what the wave heights you'd expect and the arrival times you'd expect to have at places. And so this went on shore somewhere, I think it was here, and there's some pictures online of a band playing, and all of a sudden an inexorable wave of water coming in. Not fast, just a rise in water that swept people off the stage. So you can find that on YouTube if you're sufficiently interested. So, waves. Obviously waves are kind of important to us. Where's my stuff that we were doing? This, I guess, right? All right. What else? Okay. I'm going to go back to drawing again because I think it's more instructive. Hope you agree. All right. So that's waves. We talked about viscosity. The symbol that we've given for viscosity is mu. It's not a very good mu. That's a mu, Greek mu. Its units are Pascal seconds. And the idea is that you take a fluid against a static surface. You have a plate that you put above that. And you drag that plate at some velocity x, and by applying some force on it, which we'll call S. It's kind of two-dimensional. I could draw the 2 dimensions, I guess. So it's a plate with some area attached to it. The fluid is between it, and I guess the coordinate system we'll use is x and y in this particular case. And if you pull this through at some velocity vx, then you'd expect the velocity profile in this fluid to look like this at any stage, right? A linear velocity. Linear velocity in space. And so we mentioned Newton's law of viscosity last time, and that is that the shear force divided by the area, which we'll write as being equal to a shear stress. So this is a shear stress, which we'll call tau, is equal to a coefficient, which we call the viscosity, multiplied by the rate of change of velocity in the x direction relative to, these should be partials, but it doesn't really matter, relative to dy. And so physically, what that means is if I draw on here a little diagram, this is dy, and this is dvx. So that's it. So in this particular case, this you could supplement or substitute this by writing this as mu vx y in this particular case, right? Because this is the velocity here, it's linear over here. So if you take this bigger triangle, this is vx on the top, this is y, and you get it. And so this coefficient is called the dynamic viscosity. My bad writing. And it's, as we said, its units are Pascal seconds. Kind of a strange unit. If you wanted to determine what those units were, you could just rewrite this, of course, as mu is equal to force over area, just taking this, and equal to dy dvx. And you could figure out what the units of this would be. This would be a force, F equals ma, mass times acceleration. This would be an area, meters squared. This would be a length, meters. And this would be a velocity. We don't care about the operators, we just care about meters per second. So if you substituted, I'm not going to do it, but if you substituted for this mass times acceleration, mass is kilograms, acceleration is meters per second squared, then you have it all in units that we know something about. So that's all we need to do. In past years, we've done an example. Maybe you look, I'm not sure what the timing is here. It's probably better just to explain what the process is. So what Newton's law of viscosity means is that if you take, typically you'd measure this behavior in a rheometer, something that measures the rheology of something, and you'd pull it at some velocity. You'd measure the force that you have to apply to pull it at that velocity, and then you can solve for the viscosity. You double the force that you apply on the same area, and you use that, you measure the velocity, and you use that to calculate the viscosity. And so for this, usually it's plotted as equal to shear stress. If you plot this equation here, shear stress relative to this term here. So this is change in velocity in the x direction with y. Then you can imagine that you get a variety of different behaviors. Only two are really important. This would be one. This is a Newtonian fluid, named for our guy, watching apples drop out of trees. And all that means, of course, since we know that mu is equal to tau over dvx dy, then if we look at the slope of this, didn't need to do that, then this is tau, this is dvx dy. This is equal, if you take one of these, equal to mu, and you take this as equal to 1, just from this equation here, then if you have a box here that has a unit length here, then the height of this box is equal to viscosity, by definition, right? That's all that this means. Nothing more complicated than that. So Newton's, a Newtonian fluid means that if you apply a shear stress of some magnitude here, you get a velocity on your plate of some magnitude. If you apply double that velocity, double that shear stress rather, then by definition you get, this would be V1, V2. The y isn't changing, so you double the stress, you double the velocity. Doesn't mean that it's linear related because you don't know what that velocity is, but that's the behavior you get. So a Newtonian fluid is that. And that's what it physically means, is that this equation is linear, and it goes through the origin. So you apply no stress, there's no velocity. If you apply no velocity, you don't develop a stress. Some fluids, especially in petroleum engineering, like drilling muds that you put in a hole to keep the hole open, are so-called thixotropic fluids. Thixotropic. And the more technical term is they're called Bingham fluids, after a person who thought about them. And the idea here is that you have to apply a stress to be able to get them to move. If you apply this stress here, they don't move with any velocity. If you apply this stress here, they still don't move. It's only at this they begin to move. And then after that, they behave like a fluid in movement. And so that means that they almost behave like a solid before you disturb them, because they're typically suspended clays. They make kind of a suspension. And then you disturb them, then they move. And so what we can use this for is we can solve a number of questions. I'm not going to do this today. I'm going to refer you to last year's video, because, well, you'll see that these things all occur in these. An example that we do, I think, in these fluids. An example of taking a plate that's between two static edges. Clearly, you just need to understand how to do this. The plate moves at some velocity v, so this would be the profile relative to these static edges. So this would be the velocity of the plate. If you know this velocity, it says the viscosity of this is equal to 2 times the viscosity of that. You can solve for the magnitude of the force that you have to move it at some velocity. I solved it last year in class. If you want to look at it for an example, just go back to the Zoom 2020 video and it'll show you how to do it. So if you want an example of how to do that, go there. 2 useful numbers that I skipped over. I think it's useful to know numbers for these terms. We've talked about density, water density, rock density, modulus, etc. So for water, a good number for viscosity is of this order of magnitude, so 10 to the minus 3 Pascal seconds. It varies with temperature. As you increase temperature, the viscosity becomes less viscous. So for water, this isn't a bad number to remember. It's not exactly. I'll use it often. For gases, all gases are pretty much the same, and a good number would be 2 orders of magnitude lower. Pascal seconds. Again, changes a bit with temperature, not very much, and you notice as you increase the temperature, the viscosity goes up, which seems kind of counterintuitive, but that's because there's more collisions between the atoms as you do it in a gas. So 1 goes down, so viscosity decreases, it becomes less viscous, easier to pour as the temperature goes up. Geothermal reservoirs, waters are much easier to pull out than cold aquifers, and the opposite occurs for gases. All right. And yeah, there's an example problem there. We talked about cavitation, we talked about equations of state last time. Someone asked about tables, I think appendices in the book. I don't know if they're missing in our book or not, because our book is just misses a chapter on turbo machinery and a chapter on compressible flow. So perhaps the appendices aren't in there. But download a 6th edition off the internet and you can do that for free. The last thing, I hope I'm not moving this. I guess it's kind of a bit frenetic, but that's fine. So the last thing we're going to talk about today was going to be surface tension. So we've dealt with these. Vapor pressure we dealt with in equations of state last time, kind of. And so surface tension, I used to use the venometer, but I told you last time that on Sunday I got a copyright claim to take down a video for the venometer off my site, 2 videos. I noticed that last year's video for this class, I actually did the venometer in real time myself. So if you want to see what a venometer is, to be able to measure the alcohol content in your beer, to make sure that no one's cheating you when you go to the bar, then it works on the principle of surface tension. And the principle of surface tension is essentially this. If you take a capillary tube and you push it into water, the affinity of the water to the glass is that it will, in the case of water, it's a wetting fluid, it's hydrophilic, it loves the glass, and so it climbs up it. So the water level out here is here, but inside here it loves the glass so much, it attempts to do it here, it climbs up. The amount it climbs up is proportional to the diameter of the tube. And for fluids that are non-wetting, hydrophobic, or which are hydrophobic to the quartz, which is glass made out of sand, then they want to get away from it as quickly as possible, and so they are depressed relative to the glass. And so that's just a different behavior for different fluids. So mercury behaves that way, water with glass behaves this way. The question is, what is the height that this would rise to within the tube? And the easiest way for us to do that is to just take a free body diagram, which we'll use many times in this class, and to realize, we haven't talked about it yet, but the fluid pressure at this point here, if we can make a connected path to another point that is exactly on the same level, the fluid pressure here has to be atmospheric, it feels the pressure, and the fluid pressure here has to be atmospheric here. So what we could do is we could cut this thing off here as a free body diagram that would look like, not a very good free body diagram, but you get the picture, which would be some height h in height, some diameter d in diameter, and we can think of it as a free body diagram. The free body diagram is the weight that is acting downwards, and acting upwards is the force due to the surface tension around this periphery. To make it easy, I'm going to draw it straight up, not at an angle, just because I can. And so this would be, we'll call this sigma. And so it's just a force balance. And so the force balance upwards is equal to the circumference. So it's 2 pi r, or pi d, is the circumference around here, times the interfacial tension. Yeah, bad choice. So this is, oh yeah, that is the interfacial tension. So this is the overall force upwards. Pi d times the interfacial tension. Yeah, okay. And we'll call that F if you like. The force acting downwards is going to be pi d squared, pi r squared, pi d squared upon 4, right? And it's going to be equal to the density of water, and it's going to be equal to gravity, because it's a weight, and it's going to be equal to the height. And so these, and we'll call that W. And so these have to be equal and opposite to each other. And so if we set F equals W, then we get pi d sigma is equal to pi d squared upon 4 rho g h. Let's be slick. Let's get rid of this. Let's get rid of this. And decide what we want to be able to define it in terms of. Probably we'd like to know what this term is, right? So we rewrite that as h is equal to sigma times 4 over rho g d. Which is 4 times interfacial tension divided by d times, we'll use this other term, gamma is equal to unit weight, which is density times gravity. So that's sometimes called specific weight. I call it unit weight. And it's in it's in newtons per meter cubed. So the units are newtons per meter cube. So newtons per meter, yeah, just sorry, remember that. So all this says is that the height rise is proportional to the interfacial tension. You increase the interfacial tension, which is a property of water. I forget what the number is for it right now. But if you increase that number, it'll climb higher. If you reduce the diameter of the capillary, it will also climb higher. So this height will increase if you either increase the interfacial tension, reduce the diameter of the capillary. Smaller capillaries have high height rises. A big capillary, an inch capillary, has no height rise. And if you change the unit weight, it also has to change the amount of weight it has to carry up. And so this is exactly how a venometer works. A venometer is a capillary tube. You put the alcohol mixture in it, and depending on the density of it, and depending on the interfacial tension of the mixture, water and alcohol, then it defines uniquely a height rise which corresponds directly to an alcohol content. And so look on the video from 2020 if you want to see that, because we mess around with that. And I think the question on the practice exam, which we talked about, is exactly this kind of question. So that's it. So that's how we do things. This class is kind of a frenetic one because we're switching between PowerPoint and videos and this and that. So they won't all be perhaps that frenetic. I quite like writing on the board, and so you can kind of see what the style is by looking at other videos as well. So now at the end of week 1, you have enough to do homework number 1. It's due midnight on Thursday. As I said earlier on in class, the practice exam is there if you want to do it. I don't think you need to do it quickly. It's really to let you know the mechanism by which the exam is done. So you might want to do that after you've submitted your homework assignment. The homework assignments are submitted on Canvas as kind of multiple choice questions. So don't write, you might want to write them out, but you have to submit them on Canvas. And so if people have questions about that, send me an email or ask me after class. Anything else? Any questions? Good, thank you.
Thank you.